In this video, we're going to introduce continuous distributions. Let's recall the difference between continuous variables and discrete variables. So suppose we sample 300 trees from a forest, and X counts the number of elm trees in the sample. Notice that X could be 0, we don't have any elm trees out of the 300 trees, could be 1, 2, all the way to 300. X is a discrete random variable. While Y it represents the diameter of a random tree in the sample. This is something we have to measure, and it can take on values like 7.24 inches. This is a continuous random variable. And another example of a continuous random variable would be body weights of cats in kilograms. So you have a sample of cats, you weigh them all, you have to measure it. Weights can take on values like 3.2 kilograms. And as you can see in this histogram, we have bins that have width of 0.25. For example, the first column has all weights between 2 and 2.25 kilograms. And that column represents how many cats, looks like about 28 cats, have a weight between 2 and 2.25 kilograms. So with a continuous random variable, it's impossible for us to list all the different options for that variable out on the number line. So instead we use bins. Let's see if we can find probabilities of continuous random variables and compare them to discrete random variables. So on the left, I have a computer has to pick one number between 0 and 10, and I want it to include decimals like 3.7984 or 4.77 repeating. So any real number between 0 and 10. And I'm going to let X represent the number the computer picks. And I want to find certain probabilities, like what's the probability the computer picks the number 3? Or the probability it picks a number between 3 and 6, or between 2.1 and 2.5. We're going to try to answer these. And on the right, though, let's take a look at what's on the right. So I have a hat with the numbers 0 through 10 on cards in the hat. And what I'm going to do is I'm going to randomly draw one number out of the hat, and Y represents the number we draw out of the hat. This is a discrete random variable. We've dealt with problems like this in the past, and you can see I'm asking the same questions, the same probabilities as what I want on the left. So let's start with the one on the right. Let's start with this first probability. The probability Y is equal to 3. That means I draw the number 3 out of the hat when I draw one number out of the hat. So how many numbers are in the hat? Well, there's 11 numbers because we're including the number 0. So that probability is 1 out of 11. Now let's take a look over at the one on the left. So we have, it's sort of like drawing things out of a hat, but the numbers we have include decimals. There's infinitely many numbers between 0 and 10. So asking a computer to pick a number, choosing the number 3, that's one number out of infinitely many numbers, right? So if we could put infinity on the bottom, 1 divided by infinity goes to 0. The probability that you choose the number 3 is actually equal to 0. Okay, let's take a look again at the right side. What's the probability that we choose a number between 3 and 6 when we draw a card out of a hat? So when we draw a card out of a hat, we could choose the number 3 or 4 or 5 or 6. So that means we just need to find the probability of each one and add them together. 3, 4, 5, 6, that's 4 numbers out of 11. Now the one on the left, there's infinitely many numbers between 3 and 6 when we ask a computer to pick a random number. It could choose 3, 4, 5, 6, but it also could choose 3.5, 3.7894. There's infinitely many numbers it could pick. So we right now don't have the tools to figure that out. How would you calculate that? We're going to look into that in just a bit. Now let's go back to the problem on the right. If I randomly draw a number out of a hat, what's the probability it's between 2.1 and 2.5? Well, that probability is 0 because I can either draw the number 2 draw the number 3, I can't draw the number 2.1 or 2.5 or anything in between. So that probability is 0. But the one on the left, I could draw a 2.1. I could draw a 2.2, a 2.275. There's infinitely many numbers between 2.1 and 2.5. So how could we find that probability? So you can see that these problems are different, and the probabilities are a little more challenging for the ones on the left. So let's say we ask a computer to randomly choose 500 decimal numbers between 0 and 10. I want to know, what kind of histogram do we expect to see? I actually did this. I went into Google Sheets and I typed in this formula, equals rand times 10. And what this does, the rand command gives a number between 0 and 1. And when you multiply it by 10, it brings it to a number between 0 and 10. And so I just did it in one cell, and then I copied it down, and it just gave me a bunch of different numbers. I did this from cell A1 to cell A500, so I got 500 different numbers. And then I asked the computer to create a histogram. We did this in a lab, making a histogram, and you can check it. You're going to get different numbers if you ask your computer to do this, but the histogram is going to be similar. What do we expect with the histogram? Well, this is sort of like a uniform distribution because every single number between 0 and 10 has the same probability of being chosen. But I can't list all of the numbers that all of the numbers on the x-axis. I have to put bins. So that's what I did. I asked the computer to create a histogram with bins, and I made the bins of width 1. You can see in the histogram. So it goes from 0 to 1, and we have what looks like maybe 43, 44 numbers between 0 and 1 out of 500 in my data. So if we randomly select one number x from this list of 500 numbers, let's find some probabilities. Let's find the probability x is equal to 3. Well, I went through my data and I looked for just the number 3 and it didn't show up. So that probability was 0 out of 500 or just 0. Now, what's the probability x is between 3 and 6? I can go through my data and hand count them all, or I could just look at my histogram, right? I can, on the computer, I could click on the bars and see the heights. And when I did that, I saw that the bar that goes from 3 to 4 had 49 elements in it. And the bar between 4 and 5 also had 49 elements. You can see those bars have the same height. And between 5 and 6, it had 45 elements. So to find the probability, it's just finding the proportion. You add these numbers together and divide by the total, which is 500. If you do that, the decimal approximation is 0.286. Now, what about finding the probability that if we randomly choose a number, it's between 2 and 2.5? With this particular histogram, I can't figure that out because the histogram has bins of 1, and we need bins of 5, or 0.5, excuse me, 0.5 in order to figure this out. But you can go into the histogram and edit the bin size. And so I did that, and I put the new histogram here. So I've changed the bins to a width of 0.5. And now I clicked on the column between 2 and 2.5, and there were 22 elements in that column. So 22 over 500 is 0.044. So these are the probabilities for this particular situation where I chose 500 numbers. Now let's take a look at the overall shape of the histogram. So I'm going to go back to the original one, this one, where my widths were 1. And what I notice is that the bars, although they're not perfectly all the same size, they all kind of look equal overall. Like if I was to take a step back, they all kind of look like they have about the same height. I want to create a probability distribution, which is the same thing as a relative frequency graph. Now, this is a frequency histogram because the y-axis is the number of elements in a specific bin. How I can change it to a relative frequency graph is to divide everything by 500. Now, if I did that, the actual sizes of the columns, they don't change with respect to each other. Instead of going from all the way to 60, we're going to 60 over 500, which is a number smaller than 1. But in relation, all of these columns have like the same look, and they all have the same distance between them. So it looks like the same histogram is what I'm trying to say. So when I look at this, they overall have the shape of a straight line. And if I was to estimate where that line goes, I would say maybe between 40 over 500 and 60 over 500. It looks like maybe 50 over 500. I can get the computer to give me a line. I can ask the computer to calculate the equation of the straight line. And when you do that, it'll give you 50 over 500 or 0.1. So this line kind of represents my data. And when we create a line that represents the data, we can estimate probabilities by finding the area under that line. Or if you have a different shaped distribution, if you can find the equation of the curve that describes the distribution, you can estimate probabilities by finding the area under the curve. So for example, let's say I want to estimate the probability that x is between 3 and 6. We did this earlier. We counted the bars, how high the bars were. But what we're going to do this time is we're going to think about this straight line and find 3 to 6 and shade it in. So here's 3 to 6. And the probability is, we said, is the area under the curve, which is a rectangle. So the width of the base of this rectangle has a width of 3. And the height of the rectangle is determined by that line, which is 1 over 10 or 0.1. So we just do base times height. So the width is 3, the height is 0.1, and we get 0.3. And you can tell that the bars, they're not actually all touching that line. They're a little bit shorter than the line. And so our real probability was 0.286, which is pretty close to 0.3. Let's try another one. If we find the probability that x is between 2 and 2.5, well, we can just find the width of the rectangle from 2 to 2.5, that's a half, and then multiply by the line, the height, which would be 0.1, and we'll get 0.05. You can check this with what we found earlier. We got 0.044, so they're pretty close. In general, the equation for a uniform distribution, like if you know you have a uniform distribution, then, and let's say you ask a computer to pick the numbers between 5 and 300. Whatever numbers you have, let's call the first number A and the second number B. So if A is 5 and B is 300. Then the equation of the line that represents the shape of the distribution is just you subtract the two numbers and it's 1 divided by that. And if you want to find the probability x is between two numbers, you subtract the distance between those two numbers, that's the base of your rectangle, and you multiply by the height, which is given by the equation of the line. So let me give you an example. If you ask a computer to pick one number, x between 7 and 45, then if we take 45 and subtract 7, that's 38. And so the equation of the line is 1 over 38. And I say, what's the probability of choosing a number between 8 and 10 when I ask a computer to pick numbers between 7 and 45? Well, 10 minus 8 is 2. So we'll just take 2 and multiply by 1 over 38, and we get 0.053. So in other words, there's a 5.3% chance that when I ask the computer to pick a number between 7 and 45, it'll give me something between 8 and 10. The probability that it will give me a single number will always be 0. But if you can find a range of numbers, that's the only time when the probability will be greater than 0. You always have to have a range. The uniform distribution is very common. It's a common distribution that we'll see for continuous and discrete random variables. And there's another type of distribution that's very common for continuous random variables that we'll see, and that is the bell curve. It looks like a bell. It's a symmetric graph. And so here's an example of it. Suppose we sample the heights of 3 million US adults, and X represents the height of an adult in centimeters. Notice that X is a continuous variable because height is something we measure, and somebody could be 180.3 centimeters tall. And because we measure, we're going to get infinite values. And so we would have to use, if we're going to make a histogram of all the values, we have to use bins. And you can make the bins however wide you want, but the more the thinner the bins, like if we have more bins, so the width is smaller, the more detail we have about our data. As you can see, the first graph only looks like 6 bins, and then the second graph we have more detail and so on about our heights here. Let's focus on the third one. I'm going to zoom in. And suppose we wanted to know the probability that if we randomly select a person from the 3 million US adults, what's the probability we would get somebody between 180 and 185 centimeters? That's between 5 feet 11 inches and 6 feet 1 inches. Well, all we would have to do is count how many people live in each one of these bins and divide by 3 million. But something else we could do is we could estimate a curve that describes this data. You would need to use a computer program to estimate the curve. And then you could just find the area under that curve between 180 and 185. And the computer can tell you that as well, because this one is an odd shape. It's not a rectangle, so you can't find the area of a rectangle to give you the answer here. But a computer can tell you what this is, and we will actually investigate this a little bit further, in particular for a bell curve, for a normal distribution. So that would give you a way to calculate that probability. So instead of using bars, you can use a computer to help us estimate the shape of the curve, and the probability is the area under the curve. If you've taken a calculus class, you've learned how to create these curves and find the area under the curve. So calculus is used in statistics. We won't be using calculus in this course, though.